Okay, thanks, Julia. Thanks for your kind and generous introduction. And I'm very pleased to be here to talk to this group. Although my direct research is not in imaging data, but somehow we had a application to imaging data, which I will present in the end. First, I would like to go through the methodological development. Oops. All right. Oops. So for this group, I think we already know what's going on in high dimensional data. It's a number of features or number of predictors are getting larger and larger as compared to sample size. So this is one of the way of describing the high dimensional data, that n is much smaller than p, predictors or feature, whatever we call it. So it seems like, 253 million possible predictors, protein to protein interaction. So it seems like, we need a predictive engine or predictive machine. We put all this kind of predictors one side and get the predictive modeling from outside, from the other side. It's remind me my childhood joke about it, that, two friends, two children friends, they were talking to each other. And one friend told other friend that my uncle from US sent a machine. So what kind of machine it is? He said, you put the lamb one side of the machine, you get the lamb kebab from the other side. You get the kebab from. Oh, wow, how it's possible? It's possible. And next week they met again. Now the other friend says, my uncle from Japan sent a machine, you put the kebab one side, you get the lamb from other side. So this is what's happening in machine learning things. We have millions of billions of predictors, and somehow they were able to do a predictive modeling. But the problem is, if you are dealing with so many predictors with small samples, the problem could be the bias. So suppose we can partition our parameter space beta into beta 1 and beta 2. Theoretically, we can do anything we want. So we say, oh, I partition it. And then we say that model is sparse, that beta 2 is a null vector. And P2 is greater than n. But the important features or predictors, P1 is less than n. So that's the way it has been doing in statistical learning. So I look at, it's a variable selection and post-estimation. And the post-estimation of beta 1, although all penalized method will do simultaneous estimation. So in this case, I term it as a post-estimation of important features or predictors. So we get a sum model. And some models are easily interpretable, comparing with the full models. And as we know, some model estimators are relatively efficient than the full model. The full model I'm using in the sense all the predictors in the model. So end of this story. So you started with 253 million predictors, and you end up maybe 5 or 10 predictors. You did the variable selection, you did the simultaneous estimation, and you can do the prediction. So let's dig a little bit deeper. So of course, it is a good strategy if the model is truly sparse, like beta can be partitioned, and most of the features are unimportant. So we get an underfitted model or some model or restricted model we used to call, but some models or restricted estimators are biased. It has been established even in low dimension case long time ago. And bias is the biggest problem in big data because now you have too many features, too many predictors, and you are sending them or forcing them towards zero. So we need to control the bias. So that's pretty much the message of my talk. So just look at it, how the bias come into the picture. So it should be plus sign, not minus sign. But anyway, so if you take the expectation of beta 1 hat, you partition beta 1, beta 2. Similarly, you partition your X matrix, X1, X2. So bias is this quantity. So if model is sparse, so some model is fine. There is no problem. there will be no bias and everything will work well. Or x1 prime, x2 are orthogonal, but it's highly unlikely in so many predictors you will get this condition will be justified. So in fact, there is a dominance condition. So if, for example, in simple words, if bias is small, then still some model estimator will do well as compared to if we can estimate the full model. In high dimension, we do have a problem with the estimating full model, but we can use the ridge regression to do that. I will show you. So the bias is the problem. So we need to control the bias. We cannot eliminate the bias like any bias in society, but we can at least minimize it. So bias will increase, if you calculate the MSC, the bias is the variance plus bias square without a bound. So consequentially, MSC will explode. So it's not a good trade-off in this case. So I paraphrase G.E.P. Boggs, who said that all models are incorrect, but some of them useful. So I paraphrase, all some models are biased, but some are useful for sure. So, but the problem is a naive data analyst or whatever we call them may not comprehend that the dropping X2 from the model, the impact will be drastic. So they covertly influence the estimation and testing and all of beta 1. So it's a kind of law on consciousness that we believe that model is sparse. We got beta 1x subvector, beta 1, and we can deal with it and end of the story. So that's the problem. So how to minimize this bias? So we need to find a better trade-off between bias and variance. And once again, I keep repeating myself, need to control the bias. So model is sparse, means a few strong predictors and the rest are not. That's the main source of the bias, if this assumption is not correct. So there may be weak sparsity in the model. Models may have some weak signals as well. So penalized methods generally very effective in detecting strong signals while failing to identify some weak signals by design, by the way it has been developed. So it comes back to the bias business. So we suggest a post-selection, not election. I don't know where is the S is gone. But anyway, it's election time in US, post-selection strategy to improve the performance of the lasso type estimators in high dimension strategy by combining two model estimators. So this post-selection strategy is data adaptive, and when selected, some model ignores the predictors with weight effects. So that's the idea behind it. So in terms of pretesting, we say model is sparse in low dimension. We can test beta 2 equal to null vector. Model may not be sparse, maybe to a specified vector, or maybe there is some other kind of information is available. So the idea of pretest is very old, 1944. So you have a full model, a model with, in this full model in the sense, a model with strong signals and weak signals, I call it FM. And then the model with only strong signal, I call it RE, restricted estimator, or some model estimator. I keep switching it. And then through a indicator function, dn less than equal to d alpha. So dn is test statistics. In low dimensional case, we can test it out. And then we select the estimator, but this is a new estimator. It's called pretest estimator. And we have to look at its mean square error and other things. And we see that PT is a discontinuous function of this two estimator through indicator function, and also depends on alpha. So it's, I think it's cut off. It's Donahue call it hard thresholding. So we look at a soft thresholding. Soft thresholding can be achieved through a Stein rule estimation. If you remember, it's a 50, 60 years old estimator. Through, again, test statistics, but it's a 1 over inverse function of D, so it is a smooth function. So it is a continuous function of D, and this still through a model with strong and weak signals and a estimator with only strong signals. So this might subject to some kind of shrinking problem. So we look at the positive shrinkage part estimator by taking the positive part of it to avoid the overshrinking problem. Funny is that this shrinkage positive part will dominate the classical shrinkage regarding the sign of the estimator in the shrinkage estimator. So to make sure that experimenter and data analysts don't feel strange, why we are changing the sign. So that's what it was defined to have a positive part of it. So just to give you historical background, it was the Bancroft who in 1944 suggested this estimator. So data pooling problem is also based on pretest. So nowadays we have renamed it kind of little bit different than data pooling or data fusion. It's called the distributed learning. So you are collecting data with different machines and then you are sending to one machine and you are only looking at the weighted average. Same bias problem. So that's the another area to be looked upon it, because same bias will happen because data dynamics is changing. Data points are changing every time. It's a dynamic data, so the parameters will be changing. And the combined estimator or pooled estimator or weighted estimator will be subject to bias, same like the sparsity assumption. So that's the another area. Maybe we can talk some other time. And he looked at the model selection problem at that time. And then, but the problem was, if we recall about the admissibility notions and minimaxity, the pretest estimator was not admissible. Then Stein came with this estimator. Actually, it's 1962. That's my second error I made. So it's this paper, Stein come with a Stein rule estimator which dominates the classical estimator in the entire parameter space. So entire parameter space is the important part. When we develop estimator, we have to look at its performance in the entire parameter space, not at single point. Like in simultaneous estimation and some model selection and then simultaneous estimation, we are looking the MSC at a single point, not in the entire parameter space induced by the sparsity assumption. And now we have all these regularized estimation strategies, so we can get estimators, we can get models by applying these strategies, one with the weak signals, one with only the strong signals. So we can develop this estimator. So let's look at the problem. Suppose we have P parameters and then substeps S, 1 to Pn, and then the effect of all P covariates are characterized based on their signal strength. So important predictor with the strong effects, say in S1, predictors with no effect, say S3, use this S1 and S2. I'm just bringing S3 and then we'll go back to, and S2 with the weak effect. So that's the difference. But we don't know where the weak effect will be with S1 or S3. So the original signal strength assumptions, we only added A2 for the weak signal strengths, otherwise the same, the assumptions as any penalized method. So penalized least square estimator is very simple. If n of if J doesn't belong to S1 hat, which is the estimated set for S1 with the strong signals. And similarly, we can go S1, S2, S3. And as I said, mentioned earlier, Chen, Danahu, and Saunders in their 1908 paper and Wainwright in 2009 paper argued that S2 cannot be separated from S3. And the weak signals are omitted together with the sparse signal in S3 using penalized approach. So our interest basically is improve the risk performance or MSC performance of restricted or submodel estimator in the presence of weak signals. That's all. If there is no weak signals, we are good to go. So that's pretty much what we are doing. We get a subset model or subset estimator. We want to improve its performance. That's all. In the presence of weak signals. So restricted estimator or submodel estimator can be simply done by using based on S1 hat, X1 prime inverse and usual estimator. And so this is under the same regulatory condition by Belloni and the other, I can't see the year, 2000 something. And then Liu and Yu, 2030. And actually this paper was published a few years ago based on linear model, linear regression. And the editor decided to make a discussion paper. And then the fourth group of people, they discussed our work because the bringing the weak coefficients with post estimation was probably a new idea for there. So, and then the rejoinder was also done. So this is was done a few years ago. So now the question is, if I want to do post estimation about beta 1, I get the sum model estimator by penalized method and end of the story. But then how I capture an estimator with weak coefficient? So we decided to use our old friend ridge regression, which is almost 50 years ago, which came into the picture, but people didn't realize that ridge is also penalized method, a shrinkage estimator, but it was come into the picture to deal with the ill condition for the multicollinearity problem. So it can work when n is less than p. And so in a step 2, we try to build a ridge regression, and it will take care of these 3 things. So basically, weighted ridge can be obtained by minimizing this penalty function, and then we pick the weighted ridge, and it has some more path tuning parameters, more optimization problem, more algorithmic challenges comes, and a little bit more computational complexity, but I can get a post-selection weighted ridge estimator, and which will capture the weak coefficients. And then life is easy pretty much. I can define a post-selection shrinkage estimator as I defined earlier. So the full model I replace by weighted ridge. So weighted ridge has both strong signals and some weak signals as compared to restricted estimator, which has only strong signal. And this is the distance measure for the, just like a DN in previous case, to become adaptive. If there is no weak signals, then the estimator will shrink towards some model estimator or restricted estimator. If there is a weak signals, then it will shrink towards the weighted ridge estimator, and some usual notations. So is used based in whatever we use in linear model books. And then, interestingly, we bring it to low dimensional case, and we were able to find the mathematical proof. I call it creative proof. I will tell you why it's creativity. So I can standardize, we call it asymptotic distribution risk. It's same like asymptotic risk or close to mean square, asymptotic mean square error, but it's easy to work with distributional risk in this case. So we standardize at 1 and for the benchmark estimator weighted ridge. So if you see for the sum model or restricted estimator, it's a function of delta. This delta is a function of sparsity parameter, that beta 2 is a null vector. So if delta is 0, we achieve risk reduction, which is expected to achieve. But what happens when delta is not equal to 0? That's the point I made it earlier. If the sparsity assumption is not true, the value of delta will increase, actually without a bound, and the bias will goes to large number or infinite, and so the risk or AMSC will become unbounded function of delta. So then, to control the bias, we have also calculated the risk of the shrinkage and shrinkage plus estimator. They are function of this G1 and G2. If you believe me, if you trust me, they are both bounded in delta, and they are both positive quantity. So for any value of delta, or when the assumption of sparsity moves away, its risk will be smaller than the risk of the weighted ridge estimator. And here are the value of G1x and G2x. It's possible to get it. It's not too bad. And so theoretically, we were able to show that the suggested procedure is admissible. It dominates the weighted ridge estimator in the entire parameter space induced by the sparsity assumption, and it also does better than some model estimator except near the sparsity assumption. No one can beat the restricted estimator near the, or we call it oracle properties of estimator near the when delta equal to 0. So why I call the mathematical proof is creative? Because it's a creativity. You come with a mathematical proof, but creativity is subjective. The truth is not. So I'm playing with the words. So anyway, so what do? We need a engineering proof, or we need an artistic proof. Why I call it artistic proof? Because you have control on all the simulated parameters, like an artist. When you are making a portrait, she or he has a control, make eye bigger or smaller, bigger nose, cheekbones, whatever. But the artist has to be very careful. If it does funny things, he or she may not get paid. So similarly, in simulation work, we have to be careful and need to be reasonably honest in doing that. So we generate the data, and then we look at the RMSC, relative mean square error. So weighted ridge is the benchmark estimator, which includes both strong and weak signals, if weak signals are there. And then we take the ratio. Of course, the ratio is greater than 1, means we are doing well. All right. So as I said, as an artist or doing in simulation, I can generate data. I can introduce the weak signals. So I have some strong signals, some weak signals, and then sparsity, and then no signals. And then we choose 930, and then of course, we have compared with SCAD and MCP, also LASO, and there was some tuning parameters. We try to use, as I said, you have to be honest. The same value had been used in the literature. So now you can look at the RMSC. So you look at the value of in this table. Some model estimator, this is at the delta equal to 0. Nobody can beat some model estimator when the sparsity assumption is true. But when the weak signals start increasing and then taking it over, you can see that the value of the some model estimator actually get smaller and smaller. And on the other hand, the values for MSC for the penalized method goes even below 1, come very smaller, because what's happening, the bias is taking over, and bias is making their MSC much larger. So this is the effect of the weak coefficient, and we have introduced lots of weak coefficient, 456 there with 10. So that's pretty much what we expected. Actually, this was in my mind that it would happen, and by numerically we have shown it. Whatever our conjecture, this is true. And the performance of shrinkage estimator is pretty robust. So it does very well when sparsity weak coefficients are not zero, but weak coefficient which take care, then it's shrink towards weighted range, and it still does well in all these situations. But this is good to say. You can mathematically, you can be creative, you can make a creative proof by putting regularity conditions, whatever you like. And also in simulations, you can take whatever simulation parameter, you can generate data such that it's serve your purpose. How about the data set itself, real data? We don't know whether it's a sparse, it has a strong signal, it has a weak signal, whatever. We have no idea. We cannot partition ourselves. So we have to run it and we have to look at it with this strategy. So we used this data set reported in Sheets et al. In 2006, microarray data, and it was analyzed by Huang, Ma, and Zhang in 2008. And over 31,000 probe. And let's see how many sample size was there. But anyway, in a regression analysis was conducted, and they found it 18,975 probes are important. So Huang, Ma et al., they applied the lasso and a lasso. So out of 19,000, they found 19 and 24 are important. So you can imagine. And sometimes we think, people when look at this 19 and 24, they think this 19 is a subset of 24. Not necessarily. This 19 can be completely different. This 24 selected by another method. So this is pretty much, it's hard to sometimes digest it, that what's happening. Only scientists can tell you what's happening, whether these 19 are important or this 24 are distinct than 19. So it doesn't matter, because the penalized methods are looking for reducing the prediction error. So we took this 19 and 24, and we calculated the post-shrinkage estimator. And so this time we calculate the prediction error, and once again we make our weighted ridge estimator as our benchmark estimator, because we want to capture weak signals in the data. And as you know, and people who work in genomics, they all know that most genomics data is biased. There are many weak signals in genomics data. Somebody told me, I am not a biologist or anything else, and I take whatever they say. And so let's see what happens if when we analyze this data based on shrinkage estimator as we propose. So look at the prediction error box plot on the in the plot B, and as we expected, the prediction error of the proposed estimator is much smaller as compared to penalized method. No brainer. It's, as I said, the biologists have said that the genomics data are biased. There are many weak signals. So there were many weak signals in data. I didn't know that. There is not on one, but applying my techniques, we see if there are weak signals. So if we apply this technique to a data which doesn't have a weak signal, then they will do as good as penalized method. So no problem. So this is kind of like when we used to work with parametric methods, then the non-parametric robust method came when the outliers or no outliers. So robust method does well if in the presence of outliers, and they do as good as OLS if there are no outliers. So similar situation here. So that shows that our method does very well. So this was, I promised on imaging data, so I must go to an imaging data, otherwise you will say, oh, this guy deceived us. He talked about imaging and then didn't do anything about it. So let's see. So this is the imaging data was a thesis, PhD thesis of my former student. Actually, I was co-supervising at University of Victoria in British Columbia, which is west part of Canada. Most people know British Columbia. They make lots of movies over there nowadays. Anyway, so he analyzed this data based on the mixed model, and this work was published in Entropy. So I will not go much into the mixed model. And then again, in this case, we use a generalized least square, and we also use the ridge estimator to capture the weak signals. So based on ridge and the full and sum model estimator, and same thing, we assume that model is sparse. And same way, it's just the way in my first few slides, we construct the penalized methods, restricted shrinkage, ridge shrinkage, and then the positive path shrinkage. So this is based on the ridge estimators. So you can use any benchmark, any estimator you like to construct this estimator. It can be maximum likelihood, it can be ridge, it can be OLS. And this is about the data. You guys probably know more better than this data, so I will not courage to explain this data set. So the only thing is that the students, the Eugene, he was able to get two sum models. It's only 111 subjects, and then it's 1 million of parameters. So 1.2 million or 1.2 million SNPs with 111 subjects. So he was able to get one model with the weak signal only with 100 SNPs. And so by applying multinomial logistic, he also got a model with only strong signal with only subset of 10 top SNPs. So we have two, one with 10, one with hundreds out of 1.2 million. It's a miracle. Honestly, I try to work with this kind of things with millions. And actually the machine learning people work with the billions of parameters, and somehow they come with a small number, but they ignore the bias. That's the problem. So we combine them, and then of course, we do the bootstrapping to calculate the prediction error. And in this case, we has calculated the prediction error. A smaller is the better. So RSM is the risk sum model. So sum model does well, 0.82 if model is correct. And shrinkage estimator, 0.93, and positive shrinkage, as I told you earlier, theoretically, I can show that positive shrinkage dominates the usual shrinkage. So there is no need to do the usual shrinkage, but I just put for sake of completeness, 0.92. Lasso gives you prediction error, 0.97. And on the other hand, A lasso gives you prediction error 0.98. So it looks like A lasso is a bit more aggressive than lasso. So lasso is doing a little bit better. We didn't do SCAD or MCP because A lasso, SCAD, MCP, they generally give pretty much similar results. So this is the same story that we were able to control the bias by applying this shrinkage, post-shrinkage strategy. So there are some other logistic regression model too, but in the respect of the time, I can send these slides to Julie and she can post it for the group so you can look at it. but similar result we get. So, and also there were another data set we analyzed, and for another model, so we have applied to generalized linear models and other models as well. So this is the book which I put in my reference during the, and so just instantly, I would like to say this is book with my daughter, Fayyal Ahmed, and with my former PhD student, Bahadur. He's a professor in Turkey. And so in this book, we have different chapters, even some robust method also. We apply these techniques to various chapters. And so technique is so general, so it does well in different modeling. And so we get the similar results. So you can have a look on it. So just to summarize it, that we have generalized the classical Stein rule estimators to take it to high dimensional case with the sparse model with some predictors with weak signals. So that was the capturing the weak signals. And we used the weighted ridge estimator. In fact, if you change weighted ridge by weighted ENet, so because ENet is a combination of L2 and L1, so if you take the weighted ENet in a similar fashion, you define ENet, so it's an open problem. I gave it to one of my collaborators. At that time, now he moved to another university, so the work is kind of stalled. But this is an open problem, and I think that this weighted net will do better than weighted ridge. And so there can be another story to tell. And then the existing regularized method, of course, has good advantage of generating parsimony, the sparse model, but they ignore the small contribution. You know, it's like sometimes I says, can minor sins will be forgiven? But if too many minor sins can make a major sin. So I don't know. I don't want to go that direction. So here is some references. I have an earlier book in 2014, and we have just a recent paper in Technometrics we published. Then there is another one for nonlinear models in Australian journal, and then this one weak signal assisted procedure is come in. It's 2020, I forgot. It's in biometrics, and there are a couple of we had quite a number of proceedings and special issues of some journals, Entropy and other. And I have been organizing this high dimensional data analysis conference since 2011. So that's what happened. Sometime I have a proceeding or edited volume based on those conferences. In fact, the next conference is end of August in Singapore. If you say HDDA Singapore, you will see. So this is, I think, 30th one. And just like Julie was asking for the speakers, for if next year anybody would like to organize this one, it's a well-established series. Please let me know. And life goes on. I am bragging, playing my music. So anyway, all right. So just a couple of slides, and then I will be done. You know, it's kind of a clash of cultures between statistical science and data science. In statistical science, we used to work with pre-processed sample data, exact analytical solution, low dimension data analysis. We use some packages, even R. And, you know, it's funny that I felt like as a statistician, I become idealistic. We used to say these pure math people, when we have a department of math and stats, these mathematicians are idealistic. They don't deal with the real world. When the data science came, some statistician was not very happy with this, and they become idealistic and saying, oh, well, that is not a, there is no probability statement, no this, no that, all kind of things on data science. So same thing happening to us in this way. We used to work alone or in a small team, but now, it's a domain knowledge and subject knowledge. They are both important. I have myself struggled to learn about biological sciences and other things, how things work there, and the glory of individuals. But things has been changed. We have big data available from different sources. So we need to frame the problem. Before, when I used to do consulting, I need some additional money. I will take some consulting project, and people bring the data, and I ask them, so what's your hypothesis? No more. If you are looking for a job at company, they will give you to analyze the data, and they say, frame your problem. Frame the problem so they can make more money. So identify the data for analysis, population or sample data. Sadly, the distinction between population and sample data is gone. People don't realize they are doing a descriptive analysis or inferential one. So new tools, there are so many languages or packages keep coming, and it's distributed learning, visualizing, combining data fusion. Computer science people are pretty good than a statistician. They give better names, data fusion and all kind of things. So now for a statistician, we need to do the high dimensional statistical analysis. That is the work lacking in data science. It reminds me the invention of electricity when it came in early 1800th century. It's all application for 30, 40 years. So there were people who were applying left and right. But then Maxwell equations came, and that's, made a big deal. After all this IoT, all kind of computer things, what we are having today is based on that theory. So I hope in 30 and 40 years, somebody will come and give a theoretical base to AI and some high dimensional inference, to be pragmatic rather than idealistic. As a statistician, I don't know, I call myself die-hard statistician or not, but my training was as a statistician. So to me, we must keep our core values as a statistician, which is inference. But then we must adopt. It's like a language. If a language does not adopt new words, it's become extinct. So same way we have to adopt, but keeping the core values. Core values are important. So think tanks, transdisciplinary research, and the glory of the research team. I would like to thank Dr. Julia Fisher and also my friend Ivo, who introduced me to this group, for the invitation. And thanks to all of you for sharing this afternoon with me or wherever you are. And I always thank to hardworking people of Canada for supporting my research, and they let me do whatever I want to do. So thanks to all of you again. I stop here.